All right, so be the first lecture out of chapter 11. So this chapter covers the reactions of alcohols, and so we'll split this material up into at least 3, maybe 4 lectures. So in this first part of the chapter, we're going to look at the conversion of alcohols and basically change into the OH into a good leaving group. And so we'll look at several reactions that do that. So I just summarized the reactions here at the start. So we can convert an OH to a chlorine using this reagent called thionyl chloride, or OH using hydrochloric acid, we can change that to a chlorine. And depending on whether it's primary, secondary, or tertiary, that changes the mechanism, as we'll talk about. Or you can convert an OH to a bromine using this reagent, phosphorus tribromide, where that's an SN2 reaction, so you can't use tertiary alcohols. Or you can convert the OH to a bromine using HBr. And again, so this, whether the mechanism is SN1 or SN2 would depend on whether the alcohol is primary, secondary, or tertiary. And then we'll look at how you can convert an alcohol to what's called a tosylate, using this reagent tosyl chloride. And then once you have the tosylate, you can convert that. You can do an SN2 reaction with that to put any good nucleophile in its place. So that's some of the basic reactions that we'll cover in this lecture. Okay, so if we want to convert an alcohol to a chloride, so a good leaving group, because once you have a good leaving group, then you could potentially react that with a nucleophile for an SN1 or an SN2 reaction, for example. But the point is here is that OH is a poor leaving group, right? So displacing OH minus is not an easy thing to do from a molecule, but you can convert it into a good leaving group. And so one way to do that is to react it with HCl. And if it's a primary alcohol, then this is typically, one would use a catalyst, zinc chloride, to make this reaction faster. So basically what happens here is the oxygen would react with zinc, and then the HCl so Cl minus can react in an SN2-like reaction to displace the oxygen which is attached to zinc. So you converted the OH into a good leaving group with the zinc chloride. Okay, so primary alcohol, HCl zinc chloride, will convert the alcohol to an alkyl chloride. If it's a secondary alcohol or tertiary alcohol, you might still use the zinc chloride with the secondary alcohol, but it's not needed with the tertiary alcohol. Okay, so that would convert the alcohol to an alkyl chloride. If it's a tertiary alcohol, then the zinc chloride is not needed. But the mechanism is different now. So what's going to happen is you're going to protonate the alcohol. And so now you converted an OH into an H2O, and H2O is a good leaving group. So now H2O can leave and take those 2 electrons with it to make a carbocation, and then the Cl minus can add. So we'll take a lone pair on chlorine, make a bond to that carbon, and now you have the product. Okay, so another way to convert an alcohol to an alkyl chloride is to use this reagent SOCO2. So that's called thionyl chloride. So its Lewis structure looks like that. So anytime you see thionyl chloride in this class, so predicting the product is easy. It's just going to convert OH to chlorine. But if we look at the mechanism for this reaction, so particularly interesting if you do the reaction at a chiral center. So what happens is we take a lone pair of electrons on oxygen, make a bond of sulfur, and that kicks one of the chlorines off. And some that Cl minus that just left. Cl minus can take the hydrogen off of the alcohol. So now you have another lone pair on the oxygen. And then what happens? So this leaves, but you don't make a true carbocation. Or if you do make a true carbocation, but it stays associated with this molecule that just left. And so now we take a lone pair, on oxygen, make a SO double bond, so you have SO2 gas forming, and what happens then is the Cl minus comes off. So take the 2 electrons in the sulfur chlorine bond, and this chlorine gets delivered to the same face from which the oxygen left, so you end up with retention of stereochemistry at that carbon. So SO2 gas is one of the side products in the reaction. HCl is a side product in the reaction. So you make 2 gases. So this reaction is very thermodynamically favored because you take 2 molecules and you make 3 molecules out of it, of which 2 of the molecules are gases. So that's a very positive entropy. But then our main interest is the major organic product. So you convert OH to chlorine, but you do so with retention of stereochemistry if it's at a chiral center. Okay, so if we did a reaction like this with SOCO2, then again convert OH to chlorine, but do so with retention of stereochemistry. So in this case, if you started with the cis isomer, so if it's been a while since you took organic 1, if you don't remember how to figure out cis and trans, right, OH is on top of hydrogen, and tert-butyl is on top of hydrogen, so this would be the cis isomer that you start with, and you ended up with the cis isomer, right? So tert-butyl is still on top of hydrogen, and chlorine's on top of hydrogen, so that's a cis product that you made. Okay, so if you wanted to convert to bromine, then you can use HBr, another strong acid. And so similar mechanism with the acid, with HCl and zinc chloride, but you don't need a catalyst with HBr because HBr is a much stronger acid than HCl. So you convert the OH into a good leaving group water, and then Br minus can attack that carbon and kick off H2O. And that would be an SN2 mechanism. And so the main difference being if it's secondary or tertiary instead, then it's going to be an SN1-like mechanism. So same basic mechanism at the start. You would protonate the OH, to make a molecule of water, but that's a good leaving group, so it can leave. And if you remember SN1 mechanism, you make a carbocation, and then the Br minus can add. So take a lone pair on bromine, make a bond to that carbon, and that would be your product. Okay, so if we did the same thing with this alcohol, so again, you want to keep in mind, so if it's secondary or tertiary, so you make a carbocation, and so anytime you make a carbocation, if you remember from organic 1, you should always look for carbocation rearrangement. So if we work through this mechanism, right, so you would protonate the alcohol, and then a water molecule can leave to make a secondary carbocation. And that secondary carbocation is going to undergo a carbocation rearrangement. Oops. So we'll sketch out the hydrogen that we need. So it's going to move to that carbon. And then Br minus will add. So take a lone pair on bromine, make a bond to that carbon, and then that would be your major organic product. Okay, so maybe you want to avoid rearrangement. Maybe you don't want the bromine at this tertiary center. Maybe you want it to be where the OH was at originally. So in which case you can use this reagent instead, phosphorus tribromide. So the basic thing to remember here is this will convert OH to bromine without rearrangement because it's an SN2 reaction instead of an SN1 reaction. So how does that mechanism work? So the oxygen makes strong bonds to phosphorus, so oxygen bonds to phosphorus. And then the Br minus, so we make a bond to phosphorus, kick off a bromine. And that bromine that left can come back in. So take a lone pair on bromine, make a bond to that carbon, and kick off the oxygen, which is attached to phosphorus. So basically, this is just a big leaving group. And so then the product that you make. And so notice all of this is happening at the same time. Right, the nucleophile Br minus is attacking at the same time that this oxygen attached to phosphorus is leaving, so everything's happening at the same time. That's the characteristics of an SN2 reaction. So you would make that as your major organic product, and then your side product would be that phosphorus compound. So since this is an SN2 reaction, if you remember the details of SN2, add a chiral center. So if you did this reaction with PBr3, add a chiral center, then you would get inversion of stereochemistry. Oops. So hydrogen would be flipped to the front and the bromine would be back. And that would be your major organic product. So what if you did this reaction with HBr instead? Well, since this is secondary, this would be an SN1 mechanism and this is an SN2 mechanism. And if you remember what happens in an SN1 mechanism at a chiral center, this would be something that we covered in Organic 1. Then you would get racemization. Right, why do you get racemization? Because it goes through this carbocation, which is trigonal planar, flat. So it's got an empty p orbital on there, and so Br minus, when it comes in, could attack from the bottom, which would lead to that product, or Br minus could attack from the top, which would lead to that product. So most chemists, of course, would not want to do this. They would not want to have something that's stereochemically pure and then end up with a racemic mixture. If you have it stereochemically pure, you'd probably want to be able to retain your stereochemistry. So you would probably then opt for PBr3 as the reagent so that you could either flip your stereochemistry, or if you needed to convert it to a good leaving group and retain your stereochemistry, then one option would be to use SOCO2 instead and convert it to a chlorine, which is still a decent leaving group. Not as good of a leaving group as bromine, but still a decent leaving group. Okay, so that covers the first 4 reactions here. And so the last reaction is this tosylate. So if you take the alcohol and react it with that compound, that's what's called tosyl chloride. And so what happens in this reaction is, so take a lone pair on oxygen, makes a bond to sulfur, and kicks the chlorine off. So whatever is attached to oxygen, the propyl chain in this case is just tagging along, so along for the ride. And then the Cl- that you just lost can take the hydrogen off of the oxygen. And the OH electrons will become a lone pair on the oxygen. So now you have that. Or if I draw it the way it's originally had the alcohol drawn, right, doesn't matter, it's the same molecule. Then we've converted the OH into what's called an OTS group. So this can just be abbreviated as TS. And so the significance now is the OTS group, the entire thing. So that's TS. Oops, let's do it this way. That's TS, or if we consider the entire thing, then that's OTS, and that's a good leaving group. So again, we've took the OH, which is a poor leaving group, and converted it into a good leaving group. So now you can take this and react it with any nucleophile that you want, any good nucleophile. Let's see. So just pick some good nucleophiles like potassium cyanide. Cn minus is a good nucleophile. Azide, if you remember from organic 1, SN2 reactions are good nucleophiles. Or it doesn't even have to be that good of a nucleophile because OTS is such a good leaving group. So basically any of these nucleophiles will attack this carbon and kick off the OTS group. So if your nucleophile was the OR minus, then you would make an ether. Or if it's Cn minus, you would make a nitrile. Or if it's N3 minus. So basically just take the nucleophile and put it where the OTS group is at, and that's your product. If it's a, well, OH minus wouldn't make much sense because you're just converting right back into an alcohol. Well, it will make sense if you want to flip your stereochemistry. That's what we'll show an example in just a minute. So basically whatever the nucleophile is, it just attacks the carbon with the OTS and kicks the OTS group off. So why does this happen? So let me sketch it out. So if this was Cn minus, so Cn minus would attack here and kick this off. So then that's your major organic product, and your side product is that, which is the OTS group. So why is this a good leaving group compared to hydroxide? So if this is hydroxide, then that negative charge is stuck on the oxygen, right? But if it's the OTS group, it's not, because you can take a lone pair and you can delocalize it through this oxygen to make this resonance form. Or you could have delocalized it through the other oxygen. Yeah, let's fix this. That's not right. So you could delocalize it. So you have 3 oxygens. Each of those oxygens could carry the negative charge. So you could delocalize the negative to the top oxygen, or you could have delocalized it to the bottom oxygen. So that negative charge is split over 3 oxygens, and that stabilizes the charge, so that makes the OTS group a very stable, a very good leaving group, as opposed to hydroxide, where that oxygen has to carry 100% of the charge. Okay, so if you did this reaction at a chiral center, so if we react this with the tosyl chloride, so oxygen attacks sulfur, that kicks off the chlorine, and if you notice, there is no reaction at carbon at this point. So nothing happens to the stereochemistry at the carbon at that point, because the reaction is at oxygen and not at carbon. And then we lose the hydrogen, right? Cl minus takes it. So the stereochemistry at this point is still the same, because the reaction is only occurring at oxygen. But now, when you do the next step, all right, so whatever nucleophile you choose, so when the next step is the SN2 reaction. So that attacks here, kicks off the OTS group, or if it's a hydroxide, that attacks here and kicks off the OH group. And so this is the SN2 part. So this is the stage where your stereochemistry would be flipped. So that would convert the OH to a bromine, ultimately with flipping the stereochemistry. Oops. Or in this case, you would convert it back to OH, but you would have inverted the stereochemistry, right? So here you started with a 1, 2, 3 S isomer. If you remember how to assign stereochemistry, that's priority 1, that's priority 2, that's priority 3, that's counterclockwise, so that's S, and lowest group is in the back, so it stays S. And now you have 1, 2, 3, that's counterclockwise, that would be S, but lowest group is on the solid wedge, so you have to flip the arrow, so now it's R. So you flip the stereochemistry at the chiral center for the high alcohol if you use the OH as your nucleophile to replace the tosyl group. Okay, so just as one more example. So let's see, so if we had this, so if we did this sequence of reactions, PBr3, and then let's say NaN3 minus, or this sequence of reaction, tosyl chloride, and then Na plus N3 minus. So what you would get, so this PBr3 is an SN2 reaction, and then this is going to do another SN2 reaction. So after the first step, you would flip the stereochemistry and put the bromine on, and then when the N3 minus reacts, you do another SN2 reaction, and that'll flip the stereochemistry back, and you would end up with the same stereochemistry that you started with. So this would be, so this is top of hydrogen, this is bottom of hydrogen. So you started with trans isomer, and you ended up with the trans isomer here through that sequence of reactions since you did a double inversion. But if you did this reaction instead, oops. Well, the first reaction with the tosyl chloride doesn't flip the stereochemistry, right? You just make the OTS because the reaction's at oxygen. But then when you do the next step, that's the SN2 reaction. So when this attacks here and kicks off the leaving group, then you flip the stereochemistry. And so now you would end up with that, which is now the cis isomer, right? Because this is on top of hydrogen, and this is on top of hydrogen, so this is the cis isomer. Because this is not two SN2 reactions. The first reaction with tosyl chloride is not SN2. It's when you replace the tosyl, that's when it's SN2, so you'd only do one inversion in this case. Okay, we'll stop there.